Good afternoon, all. Welcome to day 3 of RBCDSAI's International Summit on Data Science and AI. Today, the topics are going to be related to applications, and we have a fantastic lineup of speakers. First up, we have Professor Raghunathan Rengaswamy. Professor Raghu is a professor in the Department of Chemical Engineering at IIT Madras. He's also the Dean for Global Engagement. Prior to this, he was a professor at Texas Tech University and at Clarkson University, and also at IIT Bombay. He's been a visiting professor at Purdue University. His research interests are in the areas of fault detection and diagnosis, development of sensor placement, and fuel cells. He has more than 15 years and has published extensively, and he's also a recipient of the Young Engineer Award for the year 2000 by Indian National Academy of Engineering. So it gives me great pleasure in welcoming Raghu. Raghu, if you'd like to share your screen.
So today I'm going to talk about the topic of integrating domain knowledge with machine learning for actual engineering applications. So the first part of this talk, I'll talk about some of the challenges that are associated with really implementing this in industrial facilities. And to give you a flavor of how this has been done, I'll give you one example of actual implementation and building of a system that was undertaken by IIT Madras in collaboration with industrial partners. So that example will kind of anchor some of the things that we talk about in terms of challenges in integrating machine learning with domain knowledge for systems engineering applications. So before I move on, let me look at some what I call as phenotype of successful AI ML applications so that I can contrast this with what happens when we actually look at manufacturing applications. So whenever you look at successful AI ML applications, these are some of the things that are striking right away. The first thing is that the return on investment potential is easy to conceptualize and compute. So if you have an application and if it is successful, you kind of can have a ballpark of number of people who will be interested in it and the different ways in which you could be using this application. The second thing that I would say is though it's a little strong to say it's middling accuracy, but if you're not very, very accurate, you could still live with it in some sense. So for example, any recommender system which gives you some recommendations for doing stuff, if the recommendation is good, you're going to take it. If it's not good, you're not going to stop using the system and so on. And of course, if it keeps showing up things that you're not at all interested in, then that's a totally different matter. But the impact of lack of accuracy is not as much as in very critical applications. The third phenotype, that characteristic that I would say is that you have large amounts of data that is already available. And because some of these applications are from systems where data has been collected after significant ways in which you have ensured that the data that you have is good. In other words, these are directly collected from digital platforms. The data hygiene might itself not be a major concern. On top of this, the other interesting thing that one notices is that synthetic data that can augment the existing data can also be generated, right? So this is another characteristic that one sees. And the last thing that I notice is that in many cases, labeling might be available or labeling might not be a major concern. This is not to say all applications have all of these characteristics, but these are general characteristics that one looks at when one sees good applications of AI ML techniques. If you contrast that with manufacturing analytics, which is where my interest lies in, and lots of other folks who are interested in this problem, if you look at it, you will notice that manufacturing analytics is not yet a big data problem, in the sense that you do not have the kind of data that we could have for other social media applications and so on. The other problem that one sees, and this is something that we have seen every time we have tried to implement manufacturing analytics solutions, is that the data is usually in silos, which basically means that there are several systems and data is held in these several systems. And for a successful application, you have to bring all of this data into a same framework. This is something that we see all the time, because you go and an industry says that they want to apply AI, ML to their problem, and they will assure you that they have all the data that you need to solve the problem. But when someone says they have all the data that you need to solve the problem, and when you look at this from the viewpoint of actually using this data for developing applications, there is a real gulf that exists, in the sense that the data is not in the same place. Data could mean that someone knows a process which is not even being documented and so on. So that's something that one needs to be careful about. Overarching principles are difficult to identify. In other words, if I do an application for a particular industry, how do I transfer that knowledge to another industry where the design might be different, the design principles might be different, the equipment sizing might be different, and so on. So this has been a real problem in terms of showing wins rather quickly, so that people are excited about how to use machine learning AI in manufacturing applications. There is a heavy dependence on domain knowledge, both because it's not yet a big data problem. You don't have enough data, so you have to fill in the gaps using domain knowledge. And also the fact that people who have been working on this traditionally for the last 20, 30 years feel very strongly about the fact that domain knowledge is indeed needed. So that's another thing to overcome. Of course, once you build the system, then you have to really worry about the reliability and robustness. Think about saying that I'm going to implement a machine learning or AI system in a nuclear power plant, and the kind of regulatory procedures that you have to go through to prove that this is fail-safe can be pretty daunting. That's an extreme example, but this is pretty much true for everything, because as I said before, unlike a recommender system, if a thing malfunctions, it can even lead to loss of life. So it's a difficult thing to think about. And ultimately, another thing that we have learned while doing work in this area is also that it is very difficult to demonstrate return on investments, because sometimes it's not very obvious how much you get out of purely organizing your data and then predicting some things. Usually people will say, well, this happened because of something else, the market changed, some other process changed, and so on. So these are things that make manufacturing analytics difficult from an AI ML perspective. Having said this, I just want to give you one example AI ML application in this talk. And since day 3 is on applications, I thought it would be appropriate to pick one application and then show some of the interesting things that we have done, and also kind of emphasize the fact that while we do these important and interesting things, it takes a lot of work. It is not a simple application of algorithms that are available out there for a particular problem. It takes a lot more involvement if you really want to apply ML AI in engineering systems. On the other hand, this is an example that also told us that it is indeed very important to look at. Of course, we knew that, but this is as an example to convince folks that ML AI has a real part to play in complicated engineering examples, which are not highly digitized, which are not clean by any stretch of imagination, and so on. So I'm going to focus on our project on building a digital twin for aluminum smelting. Just to give you an idea, though this is an AML seminar, it's a good idea to have some background on the importance of this problem. So worldwide, from an energy viewpoint, 15 kilowatt hour of energy is consumed when a kilogram of aluminum is produced. So actually that was quite a surprising number to me. And the best performance, if you take multiple plants that run all over the world, it's about 13 kilowatt hour per kg. And this number can be anywhere between, let's say 13 is the best, on an average, maybe 15 to 16 kilowatt hour per kg. So that tells you the kind of potential that is there in terms of the savings that you can make. To give you some numbers, 2018, 64.34 million tons were produced. And this is another important fact, which is quite surprising. I think a very significant percentage of world's electrical output actually goes into production of aluminum alone. So any change you can make here can have a huge impact. So what is a digital twin? A digital twin is a model for a process. And there are multiple definitions for a digital twin. You can simply think about first principles modeling as a digital twin for the process. You can add AR, VR, and so on, and then combine everything and call the whole package as a digital twin and all that. So as far as this talk is concerned, for us, a digital twin is a model of the process where whatever changes I make to the process, if I make to this model, it should give me an output which can be compared with the process. So basically, think of this like a flight simulator. So if I do something, the flight, I take off, land, and so on. Similarly, if I add some material, increase the heat, and so on, it should say how the process will run. And that is what we mean by digital twin here. And this digital twin could be based on data, it could be based on first principles, or it could be hybrid models. Now, once you build the digital twin, the concept of this project was that you could use this digital twin to come up with virtual sensors. You can monitor and diagnose the process. And of course, with tons of data of operating this process for over years, you find out what is the best way of operating this process using this digital twin. So how you do this is all your wish list in terms of operational changes to the two process, which you don't have the time, or you might not try all of those for safety related reasons. You basically try those out on the digital twin and then see if you have some aha moment in terms of, if I operate it this way, I can get much better performance. And then once you have something like that, then you could possibly do more tests with the process and then really implement this and see whether you get something really worthwhile out of this. So that is the use for this digital twin that we started building. Now, just to give you an idea, so we said, let's start with the first principles model for this. And then anyway, once we build this first principles model, we can generate lots of synthetic data, which can then be used in development of virtual sensors, development of monitoring and diagnostic systems, which will use machine learning and AI techniques quite readily. So that was the original idea with which we started this project. And of course, the first principle models people think have good generalization capability, interpretation is possible, and so on. However, the flip side is that it is very time consuming, and in some cases, process knowledge may not be available. On the other hand, we also initially thought we'll directly do a machine learning model for a digital twin, but one of the advantages is if you have tons of data, it's a quick development than compared to first principles model. However, you might not have a physical understanding of what is happening, and the model is only as good as the data that you have. So these are things that we had to kind of trade-off, and then we decided let's go ahead and then start a first principles modeling exercise. So I don't want to convert a machine learning audience into a chemical engineering or an electrochemical engineering audience. So just to give you a picture, I'm not going to go into the details. And the next slide tells you, while it's very nice to say, I want interpretable systems, I want understandable systems, and so on. So I'm going to build first principles models. It does take a lot of effort to build these models. Just this process itself, there are multiple subcomponent models. There is a material balance model. There is a thermal model. There is a voltage model. And then for the engineers in the audience, it's also really a fascinating process. So for example, because you have a large amount of molten metal at very high temperatures, and there is current passing through this, which leads to magnetism. And because of magnetism, you have actually this material undulating. And because the material undulates, it goes back and changes the resistance, and then that goes back and changes the magnetic field that is developed and so on. So it's a very complicated process. So we did do first principles modeling for this. There are a whole set of Gori equations, which I'm going to avoid completely. And here I'm showing some results for reasons of anonymization. The y-axis have no numbers. We don't want to actually show the data, but this is the plot that you get. And when you look at it, you say, well, the first plot is a temperature plot, and I'm just showing you one case of a model fit. There are multiple cases that we tried. You see that we are able to fit a model within 29-degree error, which is not good at all. The other one is a concentration plot. And again, you see that there is considerable error. So when this happens and you have actually built a reasonably detailed first principles model, and then you kind of look at this and then say something is going on. And here is a very important thing to remember in all of this. We talk about interpretability and we talk about generalization of first principle model vis-a-vis machine learning models. And many times we fail to remember or acknowledge that the first principles models are also approximate models. So the generalization and the predictability and the physical interpretability, all of those depends on what you put into the model. Just like what machine learning algorithm you choose, similarly, what assumptions you make have a big impact and big role to play in terms of what output you get from a first principles model. So first principles models are not absolute beautiful perfect models, and this you can see quite easily here. So then you go back and then look at why does this happen and so on, and you say what are the things that I should change, what assumptions should I change so that the first principle model fits the data even more. Now what we did in this case was we built a causal graph for the whole process. And then we looked at what are the interactions and where might be the problem, that the reason why we are not getting a good fit with this. And this is a simplified causal graph. And if you go into one of these nodes, you will see a lot more nodes there. But the general idea is it is difficult to kind of figure out exactly what is happening because there is all kinds of interactions that happens. So we did try learning from a graph like this and then trying and seeing what I should change so that my model behaves better. But it did turn out that we really couldn't figure out what was happening with this. Then what we did, and there is a lot of work here, I'm going to compress in one slide because of the 25-minute talk. What we did was we looked at the data back again. So we went back to good old traditional data analytics. And then we found out that if you looked at how much alumina, which is a feed that you're putting in to produce the amount of aluminum that you need, it looked like we were producing a lot more aluminum than it is possible to produce purely from a stoichiometric balance. So here, again, imagine this we were able to do because we were both domain people also understanding data science and ML. So it's important to understand that domain knowledge plays a very important role in all of this. And this really tells us that the importance of domain knowledge in being able to massage the data and think about the data in multiple ways so that you get these inferences. Anyway, long story short, we said there is some ghost material that is coming in from somewhere. And that's not being accounted for. And that is the reason why the model is all wonky. So what we did was we really looked at where this could come from, and then we identified certain places where this could actually be happening. Now, how do you estimate how much is coming in, right? That became a very difficult question. One typical way to do this would be to run the simulation within an optimization loop and then find out optimal values for the extra material that is coming in from your data and then understand it. In this case, it turned out to be rather difficult because each of the simulations themselves, because of the complicated model, will take 2 to 3 hours to simulate actual operation worth 3 to 4 days. So if you had data for the last 2 months, you can imagine one simulation will take you about 10, 12 hours. And then if you want to put this into an optimization loop and then try to run this, it was simply impossible. So long story short, again, what we did was we came up with an approach to flip the model and then run this model in a simulation mode to be able to identify where the extra input is coming from. So this is actually some new technique we had to develop to be able to do this for this problem. So once we do this, then in this plot, you see on the left-hand side the original pictures I showed you, and then you see on the right-hand side that the predictions became really much better, and the RMSEs came down dramatically. Our original intent was to develop some predictive models with RMSE of 6 or 7 for the temperature and less than 1 for the concentration in the scaled domain I'm talking about. But we were able to achieve that. So this is all great. So where does machine learning come now? So when you do this, if you notice, what we are saying is we are trying to identify the amount of material that has come in from the data itself. That basically makes this model not predictive. So what I mean by this is, supposing I have fit the model perfectly well till today. Now I want to predict for tomorrow. I don't have any value for how much extra material is going to come and where is it going to come from, right? So again, I'm stuck with this because once it is done post facto, my model will figure out how much new material came in and then give you perfect predictions. But that's not useful if you want to use it for virtual sensors or monitoring, diagnostics, predictions, and so on. So this is where we found machine learning to be very useful. What we did was the surrogate value of the amount of material that comes in. We took data for about 6 months. For all the 6 months, we found out how much material came in, and then basically regressed that output as a function of multiple other parameters in the process. So we have a model now. Now that model can be integrated with the first principles model we have, and then we can start predicting, actually use the model in a predictive approach. Now you see how machine learning nicely combines with the first principles model. The first principles model is still the engine for prediction, but wherever there are issues with the first principle model, the machine learning model augments this and gives the information to make it truly predictive. There are multiple machine learning models that we use. We finally settled down on a on a random forest model to be able to do this, which did wonderfully well in this case. So here I'm showing you the very first attempt that we had, the second attempt, which is not a predictive model, and the third attempt now, which is predictive. But now, of course, because we are predicting, the RMSEs will go slightly over, but still we have a model which is really wonderful and which can be used for the applications that we talked about. So given that I have another couple of minutes, and if I want to take questions, let me conclude by saying machine learning models have a lot to offer in process systems engineering applications. They're very quick to develop. Sensor fusion, if you think about fusing data from multiple sensors, think about how a machine learning model will handle that vis-a-vis a first principles model. The difference is like day and night, right? Because first principles model, you need to understand the sensor, you have to model the sensor to be able to fuse this data. Whereas in a machine learning model, data is data. So sensor fusion is really simple. Of course, manufacturing is partial or limited data situations. So these are challenges in machine learning model development. I really believe the future of this field, at least for manufacturing analytics application, is to look at integrating first principles model and machine learning models appropriately. There's no blind one framework, one solution covers all approach. Each situation is different. And if you notice in our case, in this problem, this was a very complicated situation. There is a really thorough integration of first principles and machine learning models, but there are cases where you can have a much more divorced approach to integration and so on. So there are multiple ways of thinking about it, and one has to think about this smartly to be able to do this. And how to do this independent of the domain of interest is a very interesting question. So how do you do agnostic integration of this first principles model with machine learning and so on? That is a real research area in itself, and any progress that is made there can be very useful. So with that, I will stop my presentation, and I'll be happy to take questions that you might have. Thank you, Geeta. You can.
Thanks, Raghu. So, yeah, a couple of questions from what the audience have asked. One is, can these models be deployed for real-time prediction?
Yes. So these are being so. So remember, this question might be because I said it takes 2 to 3 hours. So I also mentioned that it takes 2 to 3 hours to simulate about 4 to 5 days worth of operation. Right, so this can be applied real time in that sense. So they are very fast when applied real time. But if you want to run the model so that it continuously runs to kind of predict for 10 days, then it takes 2 to 3 hours. So this is real time.
Okay, a number of questions actually have been about what is a first principle model, what is a digital twin.
Okay.
Yeah, maybe if you can just give some more clarity on.
So let me explain these two separately. Digital twin is anything where you have a computer model for something that happens in real life. So for example, I can think of a digital twin for a road, right? Which is in a real road, there are cars and buses running. So if you simulate saying, I'm going to simulate this road, so many buses will run, so many cars will run, they will be at these positions and so on. That is a digital twin for a road. So anything that physically happens in real life, if you can capture that in terms of a program, which is able to predict what will happen, then that is a digital twin. So you could have a digital twin for a shop process. For example, you say this material will move from this station to this station, and it will take so long for this to be processed and so on. So that is a digital twin for a shop process. You could have a digital twin for an aircraft. So that's your aircraft simulator. Similarly, you could have digital twins for a complete process. Let's say I have a distillation column and a reactor. You could have a model, and then you can really predict what is happening. So that is digital twin. Now, how do you model these systems so that you can predict? That is where different modeling types come in. And first principles models are models where you basically write mass, energy, momentum conservation equations. These are fundamental. And then you also write what are called as phenomenological equations or constitutive relationships. And together, they model the whole process. And this is what we typically call as first principles model.
Okay. Thank you. There was another question about, you mentioned about the energy consumption, right? After your modeling, and applying your results, how did the energy consumption change?
So I don't have the data for that. So this has to be implemented, and all of these have to be done in terms of average values, right? These fluctuate. So this you will have only after quite a bit of operations to see how much things improve. Right, and that's not an easy question to answer. And in fact, that's what I pointed out by saying at the beginning, this ROI is very difficult to compute because there are also seasonal changes around this. So how do you benchmark your solution to be able to clearly articulate what is the extra that you get is a very difficult and interesting question.
Great. I think maybe one last question. Instead of the random forest model, can any of the other deep learning models fit this problem? And one more question related to this was, can we use statistical models?
Well, statistical models, I'm not sure, because so you have to really think about. So one thing I will say about some of the machine learning models is that so you kind of feed in all the data you have and let the model figure out what is figured out. So in that sense, machine learning model is slightly easier, in my view, to implement if you know the area well. Statistical models, then you have to really do all the hard work yourself in terms of figuring out which are the ones which are important and what kind of model you're going to use and so on. So in some sense, I think you could use this, but it is a lot more work, a lot more knowledge you need. Here, you kind of feed in the data and then live with what comes out. In that sense, it's actually easier for some of these implementations.
Okay, so maybe one last question. It's been upvoted. Uh, will too much machine learning in manufacturing, reduce need for human labor?
I, I really don't think so. Not at all in the short term, because and this is something we all know, right? So when automation came in, people said everyone is going to be out of their jobs. That didn't happen, and then you had this computerization that came in on top of automation, and people said you will lose jobs. That didn't happen. Now you have on top of automation, computerization, now AI, ML. Again, people say jobs will go. And of course, if I were a machine learning guy, I'm learning from past data. Then I have to learn from past data and say it does not look likely. But as someone said, predictions are very hard, particularly about the future. So one can't say. But I don't see that there is any immediate danger in the next 10 to 20 years.
Okay, thank you very much, Raghu. There are more questions. You can go to the Q&A tab, and if you have time, you can just type your answers to this while we get started with the next one.